Can everyone hear me? All right, we are going to be starting the presentation. So, welcome to United Astronomy Clubs of New Jersey. While people are filing in and finding their seats, I do want to welcome you all here to WACNAJ, United Astronomy Clubs of New Jersey, here in Hope, New Jersey, in Jenny Jump State Park. For both people who have come here tonight and people who are joining us online, because that's right, we do live stream these to both YouTube and Twitch. So if it's ever whether you're joining us because you're out of state and can't get here, or whether you're just looking for something to do on a Saturday and can't quite make the drive out here, you can always join us online, say hi in chat, and enjoy the presentation there. In addition, you can check out our website, uacnj.org. It's where you're going to find a list of all our upcoming talks we've had in the past, links to the talks we have had in the past that we save on our YouTube channel. And it also gives interesting, fun info, like all about the telescopes we have outside that we can use when it is not pouring rain, because once again, the weather people have not smiled down upon us this weekend, and it is quite overcast and rainy. And it also has information about our member clubs, because we are actually a club made up of other clubs. And one of the best ways to get involved in astronomy is to join your local club. They're going to have all those tips and tricks for your local area that, for example, if you live in New York City and you come out here, the tips and tricks I find useful for out here probably won't work in New York City. However, we do have clubs that do astronomy frequently there, and we'll have those tips for you. In addition, you can check us out on our social media pages. We have Facebook, Instagram, we have a Discord server, all great places to find out what we're up to here at the observatory, as well as ask any questions you might have, or just show off your latest picture of astrophotography. So, since it looks like most of us have settled down in the audience here, you guys get to listen to the safety briefing. It is inescapable. I will give it now and later, just in case people sneak in. But if anyone here needs to use the restroom, that is the porta potty outside. As it gets dark, it is in fact illuminated by red for ease of finding it in the dark. When you came indoors, you also came through our little museum and gift shop area. I will be manning the gift shop counter after the presentation, because still they refuse to let me be in two places at once. They have told me repeatedly that breaks many laws of physics, and I'm not allowed to break the laws of physics, which I just think is a shame. All right. When we go to leave, we are using our headlights. We have a great record of not having people run over, and we would like your help to keep that going. As someone who has gotten run over by a car, 0 out of 10, I would like to avoid that. So let's keep that way. Just trust my experience. You guys don't need to have that life experience. In addition, we are in a state park. If we are wandering around with our flashlights because it gets dark, do try and keep those pointed towards the ground. We don't need to accidentally blind people because we're having flashlight raves. As much as the neat tricks people can do with flashlight raves, now is not the time nor place. But you're not here to hear me ramble on for forever. You're here to actually listen to Walt Windish here. And Walt tonight is giving the talk, The Beauty of the Universe. I think I got the correct one.
Beauty and Power, yep.
He does a number of talks for us here at United Astronomy Clubs of New Jersey. Walt has been interested in astronomy since he saw the Pleiades as a Boy Scout. He bought his first telescope in 1985, just in time to see Halley's Comet. Walt is a member of the North Jersey Astronomical Group and Rockland Astronomy Club. And he's been volunteering here at Jenny Jump for over 20 years. And with that, here is Walt.
Thank you. And thank you for coming out in this weather. You know, I'm getting kind of a rep for bringing monsoons with me whenever I come and talk. So I'm getting used to thanking people for coming out in this weather. How many of you are camping out? Anyone? Nice. Excellent. Some real campers out there. Well, I hope you get a great day tomorrow as well. Yeah, I'm going to talk about the beauty and power of the universe, and basically, it gives my when you leave the Earth and look out there, it's all beauty and power. It's just a totally different than the beauty we see on Earth. Brighter colors, much more violence creating that beauty. So basically, this is a potpourri of potpourri of whatever I want to talk about. I picked out some slides that I like. I try to group them together so the types of objects are together, and I hope you'll like them. As a as an ending, I'm going to give you a little preview of a talk I'm going to do in September on smart telescopes, whole new types of telescope, and I'm going to show you some pictures that I took with smart telescopes. Most of my presentations are all stuff you can find on NASA sites and other websites, JPL, Hubble Telescope, James Webb, and it's always my hope that people go home and look some of this stuff up, because it's just amazing. I love science fiction, but a lot of the stuff out there is stranger than fiction, and it's just a lot of fun to look at. So I hope you'll take some time and maybe explore one or two topics that might pique your interest. So let's start out with one of my favorites, the Eagle Nebula. This is part of the Eagle Nebula. It's nicknamed the Pillars of Creation because new stars are being formed here all the time. And it's located about 5,700 light years away from us in the constellation Serpens. And there's two side by side. There's a 1995 visible light image from Hubble on the left, and then the right one is a new one that just was released from James Hubble a year and a half or two ago. That's taken in near infrared. This is taken in visible light. Both images provide a lot of information, but with different wavelengths, you get different information. You can see you get a lot of more information in visible light from the dust cloud structures, and over here, you get a lot more information about what's beneath those dust clouds. You get to see more of the stars being born here. So when a visible light image is recorded, it's really easy to match the wavelengths of lights that are recorded to what colors they should use, right? Because between 400 and 495 nanometers is blue, and you can map out all those colors just by the wavelength that you record. But when you get to infrared, obviously our eyes can't see infrared. So the colors are all selected by the imagers who are putting that image together. They're taking the data, and they generally follow the same rule as light. They'll put the shortest wavelengths towards the blue, and they'll put the longer wavelengths towards the red. But again, this is all false color, and it's just a mapping of wavelengths to different colors. And you should understand that, especially with James Webb, because James Webb is all near infrared and mid infrared, and so none of it is being recorded in the wavelengths that the eye can see. So it's all false color images that are being mapped. They take the data and they map it. But I think this is a dramatic example of using different wavelengths to get different information about the same object, and I love that. Here's another image of the pillars from James Webb. This is a composite image of near infrared, which was the last shot we saw from James Webb, and their mid-infrared instrument, which is called the MIRI. And a combination of that data from the two infrared instruments yields us this. It's just an amazing picture. The details is just unimaginable a few years ago. So we got our billions of dollars worth, I guess. But it just illustrates how beautiful the images are out there. And it's quiet and serene, but stars are being born here. Dust clouds are collapsing, and as the gravity increases and the heat increases, they start to come alive with nuclear fusion, and they start fusing hydrogen into helium. And that's what we're seeing. We're seeing these these uh, uh, these protostars coming to life, and it's just a grand sight. The tallest column here is 4 light years, so that means it takes 4 years for the light to get from one end of this pillar to the other light. That's the distance from the sun to our nearest star, is 4 light years, and that's just this one column of gas, and giving birth to many stars. There's no stars between us and the sun. There are many stars in this pillar that are being born. And so we have beauty, and we have unimaginable power that's masked by the beauty. You'll see many orange dots. It's kind of hard when it's projected like this, but you'll see many orange dots that are newly formed stars. And on the second pillar from the top, you see something that looks like lava. These are even younger stars that are forming. Often, as stars form, they shoot out periodic ejections and interact with the surrounding clouds, and that's what we're seeing here. Almost everything you see here is local, and the pillars are just part of a much larger nebula. Here's the much larger nebula. This is the Eagle Nebula. It's known as M16. You can see the pillars there, just to give you an idea of the scale that they're looking at now. There's also a hot young star cluster here that amateur astronomers can see with even a small telescope. It's known as NGC 6611. It's a hot cluster, and it's visible modest telescopes. And remember, this is about 4 light years, so this looks like it's about 3 or 4 more light years away. But the radiation from these stars is lighting up this nebula. This is how it's getting its light. Could you imagine our closest star throwing off enough light that we can see that kind of lighting? It's just crazy. They're also sculpting these clouds. These pillars are clouds that have withstood the photoevaporation of the radiation from this star cluster, and they're taking a beating, but a lot of the dust has gone away, just like we have erosions in like Bryce Canyon. You see those hoodoos. Well, these pillars have been withstanding the radiation from that star cluster. And that ultraviolet light, as I said, is also illuminating this, and it's like a spotlight. To me, it's just amazing to think about just how much power is encapsulated in this beautiful scene. The entire picture covers about 70 by 55 light years. So this is a huge, so 70 light years for the light of this star to reach the other side. And this, by the way, this picture was taken by an amateur astronomer named Patrick Cosgrove, and he took it here on Earth. So this is Earth-based amateur photograph. I'm sure he's got some really nice equipment, but it's just an amazing picture that he's taken. So I started our journey in the Eagle Nebula because it combines the beauty and the power of the universe and time travel, right? How do you think we're traveling in time when I show you that picture? Any idea? Well, when I say something 6,500 light years away, that means it took light 6,500 years to get here. So we're not, when we look at this picture, that's not how it appeared today. That's how it appeared 6,500 years ago. We look back in time. And so when we look back at a galaxy that's 13 billion light years away, which we've done with our instruments, we're looking at something, at a galaxy the way it was only 800 million years after the time we think the universe was formed. And so we can do time traveling through the telescope. So this is just to show you where M16 is located. It's these star maps used to be really important when I started. I started out, because I'm so old, I started out in film photography, and we didn't have GPS units. And so in order to find M16, we had to look around for the brightest star around, and then hop from one star to a dimmer star to a dimmer star until we found M16. Now, with the smart telescopes and the GPS units, you just plug in M16 and the scope knows where it is and just skews over, and there you are. You got a view of M16. You got to really be determined to learn the sky when you have a GPS unit that finds everything for you automatically. It's a lot easier to learn the sky when you got to work for your objects. But folks at ACNJ here have taken many nice shots of the Eagle Nebula right from this property. Well, before we get too far out there, let's return to our own solar system just for a minute. This is a crazy picture. Does anybody know what that is? It's all the way back from 1993, but it's Comet Schumacher-Levy. It was first detected on photographs in March of 1993 on Palomar Mountain. And the magnitude of the comet's brightness was reported at 14. Our eyes can see to about 6. The larger the number, the dimmer the object. So it's a very dim object. It's about 1,000 times too faint to be seen with the naked eye. But by studying the comet's orbit back there, they realized that the comet had made a very close approach to Jupiter on July of 1992. And during that close approach, the unequal gravitational attraction, known as tidal force, tore this comet apart and tore it into 22 fragments. So tidal forces, Jupiter has so much gravity, if you come close to it, the gravity on one side of the object is less than the other side, and it can just tear it apart. That's why Io, the closest moon, has so much volcanic activity. It's the most volcanically active moon in the whole solar system, and that's because of the tidal forces in Jupiter just ripping it apart and heating it up. So this is a composite photograph of all of those fragments. So the 21 fragments slammed into Jupiter over a period of several days, centered on 1994, and they hit at a speed estimated at 36 miles per second, causing plumes thousands of kilometers high. They left hot bubbles of gas in the atmosphere and dark scars which lasted for months. It was for amateur astronomers, it was a pretty exciting time to be able to see these things. And the largest fragments were estimated at about 2 kilometers in diameter. But these scars that you see are the size of Earth. And that also gives you an idea of the scale between Earth and Jupiter. This was the first time that humans ever saw objects collide outside of the Earth, but within the solar system. And so scientists gave it the cool name of extraterrestrial collision of solar system objects. But that was a very cool time, and I'm thankful Jupiter attracted the comet, and it didn't continue on to us. That would have been a bit of a mess. Put a damper on the day. So we're going to look at some beautiful remnants that are left behind when a star dies. And this is just a chart of a couple of different sized objects. The first thing we're going to look at are what happens to a star that's up to about 8 solar masses. So a star that's between 1 and 8 times the size of our sun. It's too small to go into supernova. So what happens, as we've already seen, all stars start out in dust clouds, and depending on how much matter has congealed into the protostars, determines how large the star is. Once the radiation from the fusion balances with the gravity that wants to pull it in, it reaches what's called hydrostatic equilibrium, and that's where a star spends most of its time. For our sun, it'll be 10 billion years in hydrostatic equilibrium. It's about 4.5 billion years old. It's got another 5 billion or so to live. So you got an average star. When it runs out of hydrogen, it starts burning helium, and slowly but surely the star expands and becomes a red giant. When our sun is a red giant, we will most likely be inside of it. Like Betelgeuse would stretch all the way out to Jupiter right now. It's a red giant. So when our sun hits the red giant stage, we will be inside of it. And sooner or later, the the gravity loses in the battle with the radiation, and about half of the mass of our sun will turn into a belt of gas that'll go around the sun for about 20,000 years, 30,000 years, and then dissipate. And what's left behind is a white dwarf. A white dwarf is a star, a dead star, the size of Earth, but with half the mass of the sun. So we're talking about something that you couldn't lift a teaspoon of mass on a white dwarf, even if you could get close enough to do that. And a white dwarf will take billions or trillions of years to cool off. We don't know how long, because the universe hasn't been around that long. We do see white dwarfs though, and these planetary nebulas are just really, really beautiful. Here's one of them. This is one. If it was a clear day, I'd say you might be able to see that today. This is M57, known as the Ring Nebula, about 2,300 light years away from us in the constellation Lyra. In the summertime, you look straight up and you'll see the constellation Lyra. And if you look through a telescope, you won't see these colors, because our eyes see things like a 1/30th of a second camera exposure. So you'll see it as just black and white. You won't see the color. But what you'll see is a really cool ghostly smoke ring above your head when you look at this. And of course, there's much more exposure than our eye can gather to come up with this. This is a James Webb Space Telescope shot. There's some great Hubble images, but this is the latest. And the white dwarf is in the middle. It's about magnitude 15, which is very, very dim. But that's the star that used to be burning hydrogen and behaving a lot like our sun. The ring is about 1 light year wide, and the planetary nebula phase lasts for about 30,000 years or so. I should have put this shot in, but let me just go back for a second. This is the area that we're looking at. And this is the Ring Nebula. This is the area that we're looking at. When you combine an infrared shot, you can see how far the red giant expanded. And now that you can see even the shock waves from this thing. That was about 10,000 years before the white dwarf was formed and threw off its envelope. Here's another cool one. It's called the Hubble's spirograph. Its formal name is IC418. This was taken by Hubble around 2000. It glows like a multifaceted jewel in intricate patterns. It's just really very unusual. It's about 2,000 light years from Earth in the direction of the constellation Lepus. Here's a planetary nebula that really qualifies as a strange object. It's called the Cat's Eye Nebula. Again, it's a planetary nebula with a white dwarf in the middle, but these rings are very unusual, and there's still a debate over how they were formed. There's at least 11 of them, and they look like rings, but they're actually bubbles of gas. And NASA says it appears that the star threw off these bubbles at 1,500-year intervals. Other people think that it might be some kind of a magnetic effect, or that there might be a companion star that we're not seeing that gravitationally has affected it. But the leading hypothesis is that this star threw off these bubbles of gas. And we're looking at it like if we sliced an onion, so we see it as rings, but they're really bubbles. Each of these rings holds about the mass of the planets of the solar system, which sounds impressive, but that's about 1% of the sun. So it's a small amount, but it's still 1% of the sun in each of those 11 rings. That's about 10% of the sun tied up in those rings. So one last planetary nebula before we move on, and this is one with an attitude. It doesn't even look like a planetary nebula. Planetary nebulas, by the way, have nothing to do with planets. In the 18th century, when people like Messier were looking for comets, they kept getting confused by some fuzzy objects. And those fuzzy objects through their telescope looked like planets. They just were round. They knew they weren't planets because they were nebulous, but they knew they weren't stars because they weren't pinpoints of light. And so the name planetary nebula was given to them when we really didn't know what they were, and it's stuck ever since. But this has one of the most complex structures observed in any planetary nebula. As I said, it doesn't even look like one. And although it looks beautiful, it certainly does, there's tremendous power behind that beauty. The spectrum of its center star, which is obscured by dust, shows it to be one of the hottest stars known in the galaxy. Its surface temperature is about 450,000 degrees Fahrenheit, compared to about just under 10,000 degrees Fahrenheit for our sun. So we're talking 45 times hotter than our sun. It must have been a big star. It's estimated at about 5 times the size of our sun, which puts it pretty close to when a star would go supernova, but it wasn't big enough to go supernova. But it certainly is acting kind of strange. It's right now that star is about 64% of the mass of our sun. As I said, the central star can't be seen because it's hidden with a donut shape of object of dust. We call it a toroid. It's pinching the nebula, and you can see this dense equatorial belt of dust and gas almost edge on. The wingspan is about 3 light years. So there's 3 light years and I'm sorry, 3 light years. And they're not the delicate butterfly wings that they appear to be. They're actually roiling cauldrons of gas heated to more than 36,000 degrees Fahrenheit and racing across the space at about 600,000 miles per hour. Fast enough to get from the Earth to the moon in 24 minutes. And it's expanding at that rate 24/7. This image was taken with Hubble's wide field camera in 2009. I've displayed earlier versions of this image, but this has been reworked by the imagers and they've drawn out as much detail as they can out of it, and it's just amazing. So that's what happens to remnants of stars like ours. They blow off their outer shell, they produce a often beautiful planetary nebula, which dissipates after 30,000 years, and they spend the rest of their life or death cooling off. So what happens to bigger stars? Well, a massive star, over 8 times the size of the sun, will not stop at helium and creating carbon and oxygen. It'll keep going till it gets to iron. Iron is the first element that, when fused, requires more energy than it gives. Up to iron, they're all giving out energy. Iron requires energy, and that is a catastrophic thing to happen. Short story, and I've done a talk on the life and death of stars you could find on YouTube. But what happens is when it hits iron, the core collapses, and it just implodes on itself and creates an amazing supernova with so much energy that it often outshines the billion suns that are in its own galaxy. So it gets to be brighter than the galaxy. If it's under about 60 solar masses, if it's 60 times less massive than the sun, it'll create a neutron star, which we'll talk about first. If it's more, then you get the famous black hole. So these, as I said, these are bright. These explosions are so bright, they're visible at immense distances. And if a nearby star were to go supernova, we'd be able to see it during the day. And I will show you an example of one where Japanese and Chinese astronomers actually recorded seeing the star during the day. So this is an illustration of a red giant going supernova and leaving behind a neutron star and a gaseous remnant, something like the planetary nebula, but usually they're more intricate. So the most famous neutron star remnant is M1, which is called the Crab Nebula. This is a mosaic image. That means a lot of images stitched together. It's one of the largest ever taken by NASA. This is an amazing image of 6 light-year span supernova remnant. This one was taken in 2005. As I said, Japanese and Chinese astronomers recorded this violent event almost 1,000 years ago. In the year 1054, we have their written records of a star appearing during the daytime. And because of their accurate notes, we know that it is now what we call the Crab Nebula. So almost 1,000 years later, this is what that remnant of the supernova looks like. It's now at magnitude 8.4. It's something you can see in the wintertime with a modest telescope, take pictures of. And the neutron star embedded in the center is a dynamo that is it's emitting radiation that is illuminating this entire structure with the bluish glow. The blue light comes from electrons that are whirring nearly the speed of light, very close to the speed of light, around magnetic lines that are created by the neutron star. The neutron star is like a lighthouse. It spins around at 30 times a second. It's about 12 miles wide, so it's like the island of Manhattan spinning around at 30 times a second. So it's known as a pulsar because they spin. Some neutron stars spin 1,000 times a second. It's as I said, it's just inconceivable that something like that even exists out there. And the neutron star is an ultra dense core. It's even denser than the white dwarf. This is another composite image of the Crab Nebula from this time from James Webb, so it's in the infrared. It was released October 30th of 2023. NASA notes that the white material is synchrotron radiation, which is emitted across the electromagnetic spectrum, but becomes particularly vibrant thanks to Webb's sensitivity and spatial resolution. It is generated by particles accelerated extremely high speeds as they wind around magnetic fields. So there's all kinds of stuff shooting around here along the magnetic fields that's causing an amazing amount of radiation. We'd get toasted if we got anywhere close to this thing. And the neutron star is the bright light. I believe that's the neutron star, right in the middle of those wispy structures. So we just explored neutron stars. What happens if it turns into a black hole? That the amount of mass left behind is so great that it collapses in on itself, and the gravity doesn't even let light come out. We can't see a black hole because light can't come out. And photography and imaging is all about light. This is an artist's conception, by the way. We don't have a picture of a black hole like that. But it's meant to show how such a massive object actually bends the fabric of space-time. You can see how these stars around it are warped because they're being warped by the gravity. Picture a piece of fabric held straight, and you put a bowling ball on top. That fabric is going to really come down, and it's going to have like a cone all around it. That's very much a great example of what this black hole is doing to space-time. So a black hole will cause gravity and matter to fall into it. And although it's not possible to see the black hole, that spot where it's eating up matter is called an accretion disk. And we actually were able to image this in April of 2017 using a special uh, very large array telescope. It actually has components in Mexico, Arizona, and where's that other one? Mexico. Oh, Spain. Spain. And so they get the resolution basically the size of the Earth, and this astronomer came up with a program to actually assemble this data, and she published it about a year afterwards. Just amazing. So we're the most accurate way to describe this is we're seeing the silhouette of a black hole, because we can't actually see the black hole, but we can see all the matter and where the hot spots are as this matter is whirling around and getting sucked up by the black hole. And this particular black hole was in the heart of a galaxy called M87, about 55 million light years from us, and it was taken over the course of 4 days. And again, what we used to get this, the process is called very long baseline interferometry, and it's as I said, we're measuring the wavelengths across the entire Earth basically. Now there's a phenomenon that Einstein predicted would come about from black holes, called gravitational lensing, and we finally proved that it's true. In 1979 we observed this. With the advent of the Hubble telescope and now the James Webb Space Telescope, we've been discovering more and more instances of this phenomena. So what gravitational lensing is the black hole and dark matter in a large galaxy structure warp space-time so much that you can see what's directly behind it, because the light doesn't come straight out. It curves, just like that bowling ball curved the fabric that I was talking about. And so we see these very distorted images of galaxies that are very far away, but they're also magnified. So this is a gravitational lens caused by a galaxy structure located about 6.3 billion light years from Earth in the constellation Coma Berenices. And the lens these galaxies created greatly amplified an even more distant galaxy that we call the cosmic seahorse galaxy. And combined with Webb's incredible resolution and sensitivity, this technique has allowed astronomers to study a galaxy they would never be able to study if it wasn't for that gravitational lensing. This is another really cool picture. This is a gravitational lensing, and it creates an Einstein's cross. And there's one quasar behind this very massive galaxy group, and the light from the quasar found 4 different paths around it. And so we're seeing one quasar at slightly different instances and different magnifications as it bends through space-time. This is like mind-blowing stuff. There's also a picture out there that they took years earlier of a supernova, and it's the same thing. It's an Einstein cross. It's one supernova, but they saw it at 4 different, slightly different stages of it exploding. Quasar stands for quasi-star. Before we knew what they were, we said it looks like a star, but it's super massive, and so they named it quasi-star, and it kind of stuck. We now know that they themselves are super massive galaxies with giant black holes in them. So the quasar here is about 8 billion light years away from us. The galaxy that's doing the lensing is only about 400 million light years away from us. So it's 20 times closer to us than the quasar. And it's bent that path so we can see the light come in 4 different images. Here is a totally different object. This is the Pleiades. I don't know if you've seen it. It looks like a little dipper, and you see it in the winter sky, and It's also known as the Seven Sisters because there are the seven brightest. There's actually about 3,000 stars in this cluster. It's known as an open cluster. And reflection nebula reflects light from the star. There's two kinds of nebula, reflection and emission. A reflection reflects light from the star that's nearby. Emission nebula is when there's so much radiation coming into the cloud that it excites, it ionizes the hydrogen alpha, and actually glows, and so that and the emission nebula is usually red in color, and a reflection is usually blue. And so this is blue. We used to think that the clouds around these seven sisters, around the whole Pleiades, was associated with the birth of those stars. It was the remnant gas from the birth. But we now know that it's really a bunch of clouds that are passing in front of the Pleiades, and it's not actually part of the birth of those stars. The clouds are going by at 18 kilometers per second, which is, I mean, can you imagine if you saw one of our clouds going at 18 kilometers a second? The scale of this is just amazing. So that's the Pleiades. So what I'd like to do now is show you a couple of pictures that I've taken myself, and I hope to just encourage you maybe to try it. The stuff I'm going to show you is taken with equipment that won't that's not thousands and thousands of dollars. Although I warn you, if you try one of these things, you may end up spending more than you'd want to after you catch the fever. But the first thing I did back in the film days was I made this thing called a Scotch mount, or a barn door hinge. And this, when you take an exposure with a camera longer than 30 seconds, you've got to compensate for the rotation of the Earth. Somehow you have to keep the camera moving at the same way that the Earth is, or you're going to get really streaks. Like when you see those star trail pictures of, the big trails, that's just keeping a camera stationary and letting the stars go around it. But if you want to get something where the stars aren't moving, you've got to do something. And there's plans for this all over the internet. Scotch mount, barn door. Now that you can get trackers for like $200, I'm guessing a lot of people aren't crazy enough to build this stuff. But do the math, and there's just a carriage bolt, and there's a crank down here. See this carriage bolt? There's a crank, and if you turn the crank once per minute, it'll track the rotation of the Earth. And what I did, and again, this is before the internet, so I had a radio that had a time station that clicks off the seconds, and every 15 seconds I turn the crank a quarter turn, and so four quarter terms. We'll do that in a minute. And I just mounted a camera with a 50 millimeter lens, and right from here I caught Comet Hale-Bopp. This was a scan photo. I really have to spend, I hate post-processing. I'm just so lazy. I hate post-processing. I gotta punch that up, but you can see very clearly the comet, and the stars are pretty good. There's a little, but for a 4-minute exposure, I think that came out pretty good, especially with a 50 millimeter lens instead of a wide angle lens. So as I said, that was taken right outside this house. The Minolta camera, if you were to buy this equipment yourself, you could probably get it, the digital equivalent, you could probably go for like $300. It's not that expensive, and you can start taking pictures. This is a better picture. I didn't take this. What I wanted to show you, it's the same picture of Comet Hale-Bopp. By the way, that other picture was a 4-minute exposure taken in April 5th of 1997. I just want to show you, this Comet Hale-Bopp was a great example of the two tails of a comet. And you can learn stuff about the comet just by looking at its tails. The ion tail is much lighter material, and so it's strictly affected by solar winds. And so wherever this tail is pointing, you can find out where the sun is. You just follow the ion tail, and you'll know the sun is somewhere there in the picture. The dust tail are heavier particles. And so they're not only affected by the solar winds, they're more affected by the motion of the comet. And so the way, when you see the separation here, you can tell this comet is moving in this direction because this tail is lagging the ion tail, the heavier tail. So you can tell two things just by looking at the tails of a comet. You can tell where the sun is and which direction it's moving in the sky. Next, we'll take us to 2004. I took this photo in Vermont, the April eclipse last year. And I have to admit, I did use a fancy telephoto lens, but you could come very close to this with a camera rig of about $500. The most important thing is get yourself a good solar filter, right? They're $50 to $100, and you can even take sunspots with this. But I took this. There was no tracking device. These were short exposures, and just my camera with a telephoto on a tripod. And it took me this long before I bothered to see a solar eclipse. And I got to tell you, I wish I had gone earlier. There's nothing like it. And the difference between 99% and 100% is literally the difference between day and night. You got to see a total. But when you get to the point where you can take your glasses off, and I saw these eyeball. Remember, this is the moon covering the sun. So the size of this image to your naked eye is the size of the moon. And so it was just amazing when that moon moved right in front of the sun. To see solar prominences like this, naked eye, it was just astounding. It was, I just can't. So much going on. A little wind kicked up. It got dark. It's just a very strange, eerie feeling. And again, you can take pictures. This is another showing the corona a little higher exposure. This is the classic engagement ring. It's just as the moon moves off, it creates like a wedding ring look. Now, of course, this isn't everyday astronomy. You got to find a solar eclipse. Just like the other picture I showed you, got to find a comet to take pictures. But this baby has really changed my view of astronomy. This is called the C-Star 30, and I ordered one last October. It was $349, and now they're $399. And this is an all-in-one scope. They even give you a little tripod. I like to put it on a camera tripod. And this is someone else's picture of it. I was too lazy to set mine up to take a picture for this, but I will have them on my talk in September 17th. But anyway, I got this delivered in January, and immediately went out. There's no eyepiece on this telescope. It's a 30 millimeter opening. There's all the electronics are in it. You just level the thing. It has a catalog of stars, so it knows where it's at. After it orients itself in a couple of minutes, you just tell it where you want it to point to, and you control it with your iPhone, your tablet, whatever, and it takes pictures. It's just amazing. And I got this, I gave this its first light in February on a really cold night. Once I set it up there and leveled it, I sat inside and had dinner, and I just watched the pictures. What it does is it takes 20-second exposures and stacks one on top of the other digitally. So when you're looking at your phone, you're seeing the noise level of the background go down, and you're seeing the image come up. And there's smart telescopes that have higher resolution. I mean, this is the least expensive one right now. It also has probably the lowest resolution, but I got it because I could put it in my travel gear. I could pack it on an airplane. And the funny thing is, I didn't know when I ordered this in October, but in January I got a call from my son telling me he's taking me to New Zealand. And wow, what do you know? I put that in my carry-on, and I took it along with me. It wasn't a planned astronomy, so it was like 10 days before the full moon, not the best time to go. But it was a family vacation, but I just set this thing up and took some pictures. So the first picture I took with this is the Orion Nebula. And this is on the walk in front of my house in Wayne. So we're not talking about super dark skies. We're just talking about set it up. I turned the front light of my house off, and I set this thing up. 26 minutes. So 26 minutes worth of 20-second exposures, and there's the Orion Nebula. And again, this is just a little taste of the talk I'm going to do on September 17th. I'm going to be talking about $400 smart scopes, $4,000 smart scopes. So just a little shameless self-promotion right now. But the images I took certainly fit in with the beauty and power of the universe. This, like the Eagle Nebula, is a birthplace of stars. There's a lot of stars being born here. This trapezium is a very famous and overexposed in this picture. But this is amazing. This is a $400 telescope, and it just sticks the image into my photo gallery on my iPhone. It's just amazing. Again, no eyepieces. You just look at your phone. Now notice the orientation of the Orion Nebula. There it is. There's a shot from New Zealand. Now I'm in New Zealand, and it was kind of weird. I'd been to Rwanda on a mission trip, but that was the only other time that I was south of the equator, and New Zealand is way down under. And just seeing Orion standing on his head, and it took a while, and then seeing stuff that you can't even see here was just a bit disorienting, but it was a great time. And this was a dark sight, but this is only 8 minutes worth of data. 8 minutes, and that's what I got from the Sea Star. It's only 8 minutes because there were so many things that I couldn't photograph up north. I didn't want to waste all my time on this guy who's out my back door all the time. So I took a few more. This gorgeous cluster you can't see up here. It's called the Jewel Box cluster, or Caldwell 94. It's the same type of object as the Pleiades. It's an open star cluster. This is a very young star cluster, though, 16 million years old, which is that's still in diapers as far as astronomy is concerned. There's about 100 stars in this cluster, very predominantly blue and very hot. And it's naked eye object, but it looks like a star when I was looking at it. This cluster is about 6,500 light years from Earth in the constellation Crux, the Southern Cross. And these clusters are great targets for scientific observations because they're all formed in the same giant dust cloud with the same general chemical composition, but varying sizes. So it's a great cluster for scientists to study. And these stars will only stay together for a limited time, and slowly they will kind of drift away like high school buddies. This was one of my favorite objects I got to photograph. Omega Centauri. There are almost 200 globular clusters that surround our galaxies, and they're very tight. Compared to the open clusters, a globular cluster is a very tight association of stars. This is called the Omega Centauri globular cluster, or Caldwell 80, and it lies about 17,090 light years from us in the constellation Centaurus. It's the largest, most massive globular cluster in the Milky Way. This is it. You can't see it from the north. You got to head south, and it's a naked eye object. You can't see that naked eye, but you can see an extended object naked eye. This is about 450 light years wide. Amazing object. Globular clusters are much tighter and more massive than open clusters. The Omega Centauri is estimated to have 10 million stars compared to the Jewel Box's 100. And another contrast is that they are mostly old stars. Other globular clusters are even more homogeneous in that they have old stars. This one's a little unusual because this big boy has some variety of age, and that's kind of unusual for a globular. Here's another one I took. This one, those other ones I did no enhancement to. Those other pictures you saw, I did no enhancement. I just took what came out of my C Star 30 in my phone. This one, I intensified the red a bit just so you could see it better, and I fully intend to play with the other ones. I've just had a busy season right now, and this summer is when I hope to maybe do a little more post processing. But yeah, you can take these pictures of the C Star and put it in Photoshop, or they have some free astronomical software, and you can stretch it and bring the color out. So what you get from the C Star or any telescope really is your raw material, and then you work with it. Some people make it, process it so much it looks cartoonish. I'm not crazy about that, but it's up to your eye, whatever you like. It's your image, and it should look like something that you produced. So this is NGC 2244, which is the satellite cluster. It's actually an open cluster like the other ones we've seen, and it's got the Rosette Nebula around it. It's I believe the Rosette. I think that's an emission nebula. I'm pretty sure it's an emission nebula. It's in the constellation Monosaurus, and there's a few really hot and active O stars, which are the hottest stars there are, and they generate a lot of stellar wind and radiation. Yeah, so the radiation is what would excite the hydrogen alpha and ionize it, and so this is an emission nebula. See, I'm not too. This one I think you can photograph here. I have not done it, but this one I think is reachable from this latitude. So those, just a teaser. I'm going to have a whole bunch of images taken with smart telescopes, both this telescope and a $4,000 smart telescope made by Celestron, and we're going to talk about doing smart telescope astronomy or electronically assisted astronomy. That's not astrophotography. It's using a screen and one of these telescopes to show other people. So if I'm going to a Boy Scout meeting and I want to show them the sky, instead of having them line up at an eyepiece, I now can have an iPad and show them exactly what it is, and they can see the image building with color, which you can't do when you look through a telescope. Again, you're going to see mostly milky colorless images when you look, unless you're looking at a planet, right? You can see color on Jupiter and the like. So a whole new era of astronomy, sidewalk astronomy and astrophotography is coming around, and it's pretty excited because I'm lazy by nature. And an astrophotography rig is, you got a telescope, you got a guider scope, you got wires all over the place. This thing you just plunk down, align it, and you're ready to go. It's beautiful. So this summer, my grandson and I will be collecting data for the presentation in September. I've got a lot more images to take. I'm going to do side-by-side images with a $400 scope and a $4,000 scope, and it should be fun. It should be fun just putting that talk together. So I'll leave you with one last image. It's called Gravity's Grin. That's another gravitational lensing. You can see these two galaxies that are colliding. There's so much mass here, including dark matter, that we see some gravitational lensing. So these are galaxies that are far behind this galaxy group, and it just so happens that it frames kind of a face. This purple there's so much radiation being created here by this by the two large elliptical galaxy eyes that we're seeing a whole bunch of X-ray glow, and that purple is X-ray glow. The collisional speed between these two eyes is about 1,350 kilometers per second. So it heats up that gas to millions of degrees, and we see that in the purple glow of the X-ray image. The Cheshire Cat group can be found in Ursa Major, which is the same constellation that holds the Big Dipper, and it's about 4.6 billion light years away. So thank you so much for coming out and listening.
All right. Thank you, Walt, for another great presentation. So we are going to be doing a question and answer session. So I think since no one looks like they've snuck in, uh, because I get to sit in front of the door, so I could know that this time. I don't need to do the safety briefing again too extensively. However, just reminder, we are using our headlights, and any flashlights do point that toward the ground. If you need to use the restroom, that is the porta potty outside, illuminated by red. So how question and answer session's gonna work is for people here. You get to raise your hand, and I pass you the microphone. The microphone is so that we can hear the question, and chances are, if you have a question, someone has a similar question but might not be uh, brave enough to ask that. Online people, you get to just type in chat because that you got the easy job. So I'm gonna start us off with our first online question is, how do we know how far away the Eagle Nebula is?
There are a number of ways, but redshift is the main way. There's something called the Doppler effect. If you're at a racetrack and you hear a car coming towards you, you hear the pitch of that car go, increase in pitch, and then it goes away. It's like boom, right? And that's because the sound waves are being stretched. And when it comes towards us, that's blue shift. So if something's moving towards us, like the Andromeda galaxy, there's not many things moving towards us. Most stuff is moving away. But there are a couple things. That light would be shifted towards blue. And the reason why we know the light shifted towards blue is because we know the spectrum of the elements that are in those stars. And those are very specific bands of color. And so when those bands of color are shifted to the red, then we know that the object is moving far away from us. The amount of shift tells us how far that galaxy is. And so when you have a galaxy like 13 billion light years from us, 12 billion light years from us, that redshift, they call it, is a redshift of 7. And so by the amount of the amount of shift in that light, we can tell how far it is. We can also use Cepheid variables to help us pinpoint how far that galaxy is.
Question out here.
Thank you. How long do supernovas last?
Well, the remnant will last about, the remnant will last about 30,000 years. You're talking about the supernova itself can be seen for a number of days, and then the light gradually decreases. The actual neutron star left behind will take trillions of years to dissipate. Right? It's no longer nuclear fusion, but it's going to take a long time to cool off. The gas cloud that's left behind will dissipate usually in about 30,000 years. And of course, with the black hole, Stephen Hawking has this black hole evaporation, but it takes trillions and trillions and trillions of years for a black hole to evaporate. And I don't understand the math, and I won't pretend to. But yeah, those stars that are cooling off, even the white dwarf, take a long time to cool.
All right. So our next online question is, does Walt have any images from the film astrophotography era?
Well, that Comet Hale-Bopp was on 400 ASA, not ISO, ASA Kodak film, and yeah, I do have some.
All right, and we had another question back here.
Hey, Walt, on your eclipse photos, I noticed some color on that. What solar filter were you using? How'd you get color there?
I was using a Thousand Oaks optical, and it was a screw-in filter, and I had a 100 to 500 Canon telephoto, and it just screwed into the top, and yeah, that color was just so brilliant. It came through. It was amazing.
Right.
So wait. You know what? I think I'd have to look at I think I unscrewed the filter just as it reached totality. I bet that's probably what I did. Yeah, I unscrewed that filter for the I think it was 3 minutes and change of totality, and took pictures without a filter on it. Yeah. Yeah. Good point. Yeah. I definitely took that filter off and just photographed without it. And you know, that's a nice thing about the having a electronic viewfinder, because if you mess up and mistime it, you know, if you mess up with the sun and you get sunlight through a telephoto lens or a telescope for even a second, and I know a guy who lost sight in one eye from this, I'm telling you, you cannot react fast enough. When you're looking at the sun, it's dangerous. And so with the electronic viewfinder, if I mess up, light isn't going into my eye, it's hitting the sensor, and I could damage my sensor, so I got to cover it up, but it's not hitting my eye because I'm not looking through an optical sensor. I'm looking at an electronic viewfinder. So that's a pretty cool thing about using that for eclipses.
Yeah. Especially when you're viewing through optics with your eyeballs, at the sun, you're giving your eyeballs the ant under a microscope treatment, and many people know what that treatment is, and you should not do that to your eyeballs. So proper filtering, always a must.
Know what you're doing before you do solar observatory. You can be crazy out in the night sky. You'll learn the hard way, but you don't want to learn the hard way with solar observing.
All right, so our next online question is, what would have happened if one of the fragments from Shoemaker-Levy hit Earth instead of Jupiter?
We'd have some big problems. I mean, if you get a 2-kilometer fragment hitting Earth, I mean, that would just, it would raise up dust throughout the Earth, and who knows what it would, maybe it would cool down the Earth a little bit, but it would not be a good thing. It would be catastrophic.
All right, was there another question out here? All right.
You mentioned before that you stack up different photos with different exposures, like together to create one photo. Is that different from HDR? Or is that like the same thing?
Yeah. No. What HDR does is it takes 3 or 5 photographs at different exposures, and it stacks them, so you get the detail in the dark and you get the detail in the highlights, right? It actually looks a little false. I'm not crazy about it, but sometimes I do use it. But what stacking does is all of these photos are the same exposure, but what you're doing is you're just gathering more and more data, and then you're stacking all that data, and it's amazing to think that you could take all these 20-second shots, and when you stack them, you have so much more information in that resulting JPEG. But yeah, all you're doing is you're stacking data on data. Some of these guys here, they'll collect like 5 or 10 hours of data in like 1-minute exposures, and then they'll put it together. Also, there are programs that will take out bad exposures. Like if you have a plane going through one of your 20-second exposures, the software usually will automatically drop it. And if you're taking pictures of Jupiter and the scene is not good, someone that's like kind of wavery, it'll take the best exposures and discard the ones that are a little blurry, so you can really increase the sharpness of a photograph and the detail and the color. It's an amazing process.
Yeah, because if you have a lot of short images, you get nice pinpoints, but as you start getting into the longer, unless you have really excellent tracking, you can start running where you start getting a little bit of trailing, especially if you happen to line properly, and then you start getting like little rings and little dashes as things progress across the sky. So they're trying to get that as if they had that really long, nice exposure, but reducing the amount of potential error and problems they get. All right, so our next online question. Do you feel like the investment we've made in planetary defense are sufficient to respond to the threat suggested by a comet impact?
I have no idea. That's beyond my expertise. I don't know what we're doing and what we haven't.
Well, have we
Oh,
gotten
wait, have you said, wait, I'm sorry, I thought you meant like wartime. You're talking
no,
about
Schumacher Levy
We have-
decided
2 years
Earth
ago.
looks prime instead of Jupiter.
2 years ago, we sent up a charge that was the size of a refrigerator, and we hit an asteroid with it, and we definitely moved the course of its orbit. We changed its course, so we know that the technology does work because NASA actually did it. You could Google that.
It is the DART mission he is referring to.
There you go. So we know that we do have the technology to at least nudge something off.
All right. Was there? Oh, I see a hand all the way in the back. I knew my steps.
Just wanted to note the difference between the question and your answer, that you indicated a mission to an asteroid, and the question was about a comet. And there is a significant difference between those two objects.
That's true.
And especially their defensibility.
Yeah, absolutely. One results in a bunch of gravel, the other gets a snow cone. But no, you're absolutely right. They do. Yeah. A lot easier than a comet. Yeah. And of course, the closer the comet gets to the sun, the faster it's moving. Right? So it's changing speeds as it whips around the sun. Good catch, Paul. Thanks.
All right. So our next online question is, why is the explosion pinched by the ring of dust? Why didn't the explosion blow away that ring? I think that was
The Butterfly Nebula.
yeah. I was like, the one that was all red. Like, there were a couple of them.
There was no explosion because it's a planetary nebula.
That wasn't.
No, it looks like right. It's a very strange looking planetary nebula. But remember, a planetary nebula does not have a supernova explosion attached to it. It blows off its belt, and I don't understand the dynamics. I'm sure they're still studying just exactly because it looks like almost like relativistic jets, which they're not because they're not moving fast enough. They're just jets that are being jets of gas that are being positioned in two different directions because of that toroidal shaped gas ring around it. But there was no supernova explosion to blow that dust out.
All right. So online people, I'd like to give you a chance. If there's any last minute questions, do get those in. I like to give them a little heads up because by the time we're 2 minutes into the future, they finally get that message because stream delay is a thing. Right. Was there another question out here? Bueller. Right. So our next online question. Walt, you mentioned turning the front light of your house off to use your C-Star. Is your home lighting dark sky friendly? And where can our guests go to learn more about reducing light pollution?
Well,
Thank you, Dan, for the insert lighting.
Yes, I actually paid like $60 extra for a dark sky friendly light to go into my fixture, and it's not always available. There's a National Dark Sky Association. If you Google that, you can see all kinds of ways to make your lighting more dark sky friendly, so that stray light doesn't shoot up. Get away from sodium lights, those yellow lights that are just all over the place. Encourage your town to do the same.
The biggest thing, put your lights on timers or switches because you don't need permanent all the time on, and just make sure you use directional lighting. You don't need to flood out the entire neighborhood with your lighting when you could just use a flashlight to poke your head out the door to look at the raccoons vandalizing your trash can. You know they're at your trash can. You can see them with flashlight. You don't need to light up your next door neighbor's house as well. Questions? All right. So it looks like that has finished up the questions. Just to give them a few extra seconds, I do want to thank Walt here for another great presentation. I want to thank you all who have come here on site and online, joined us in the online chat room. Thank you so much for joining us here. W- we greatly appreciate the support. Online people, if you hit those like, follow, subscribe buttons, all free actions, it does help us keep going, keep our outreach going. We are a nonprofit, so any amount of support does help going to keep the bills getting paid so we can keep offering these free programs. As the infographic, you can check us out on our website. We have many social media and whatnot. You can also check us out and keep up to date on what we are doing. With that, since it looks like we're all done with questions, I want to wish everyone clearer skies and better seeing than we have been the last few Saturdays. Good night.
Thanks.